Hello, my name is Francesca Cairoli, and in this video I'm going to present this paper about neural predictive monitoring under partial observability that I've done in collaboration with Luca Bortolussi and Nicola Paoletti. So the paper focuses on the problem of predictive monitoring for a cyber-physical system with a safety critical component. And predictive monitoring itself simply aims at preemptively predict if a safety violation is about to happen in a short future. But we are also interested in a more realistic scenario in which we don't have access to a full observability of the state, but we can only have information about a partial and noisy measurement of it. So in general, predictive monitoring can be formulated as a reachability checking problem, which means that we are given a certain time horizon and a certain region of states, and we check if from these states we can reach or not an unsafe state. The analysis itself may take a lot of time and is typically done offline. However, we want our technique to work at runtime, so as the system evolves. And therefore, we need this monitor to be efficient, but still we want the monitor to be accurate. So we don't want to lose safety, but we need to have quick answer so that we are able to make some action that prevent the occurrence of the failure. So in order to reach this trade-off between accuracy and efficiency, a previous work proposed to have a learning-based method for predictive monitoring. The idea is very simple. We propose we approximate the reachability checker, and by formulating a supervised learning problem in which the reachability checker is used to label states that are randomly selected as safe or unsafe. So we randomly select a state from the state space, we label it as safe or unsafe, and we actually have a binary classification problem. So we take this data set and we train a neural network to generalize over the entire state space so that we are able to make prediction also about unobserved states. In our setting, which is a partial observable setting, we cannot query the oracle about the safety because we don't have full information about the system. So it is necessary to introduce a state estimation step. However, the state estimation step is going to introduce some errors that are going to be propagated together with the approximation of the monitor. So prediction errors are inevitable and they also have a sort of complex nature, but we also are moving in a safety critical domain, so we need to have some guarantees about the performance of our predictive monitoring. So the idea is to try to prevent the errors that are detectable, and in order to measure the reliability of a prediction, we are going to use a well-known technique called conformer prediction that is able both to quantify the uncertainty of a given prediction and also to provide additional statistical guarantees about the prediction itself. So a little bit of formalism is that we are actually focusing on deterministic systems and that have a sort of combination of continuous and discrete dynamics, and we have to model the observation function. So we model it using an observation function mu that maps the full state into the partial one, and then we add some additional measurement noise that follows a distribution W. And we're going to use this model to build a synthetic dataset. So the dataset is made of a history of states, a history of measurements, and a label that says safe or unsafe. And the idea is that we are at time t in this state, and we simulate backwards and forward, and we use the information about the past as input, and the information about the future is going to be used to label the state as t as safe or unsafe. And using the measurement model, we also obtain the sequence of measurements, right? So we have a tuple of 3 entries. And in our paper, we propose 2 alternative approaches. So given the history of measurements, we can decide either to learn directly the mapping from the measurements to the safety label, or we can decide to have a 2-step approach in which we first reconstruct the full state of the system, and then we map this sequence of reconstructed states to the label, reachability label. In the first case, the end-to-end solution, we just have to train one-dimensional convolutional neural network, since the horizon is fixed. And in the other case, we have to train a regressor, and which is called neural state estimator, and a classifier, which we are going to call the neural state classifier. And then we combine the 2 neural networks, obtaining a mapping from YT to the label. And we perform a fine-tuning of this combined network, so we define a composite loss. And the idea is that by doing this fine-tuning, we make the composite network, we make the neural state classifier work better on reconstructed states and not on real states. And also we allow the neural state estimator to be more precise on those regions of the state space that are more safety critical. So this fine-tuning step improved a lot the performances. And as I said before, now that we have the training phase outlined, we want to be able to measure and quantify the reliability of the predictions. And so this is why we introduced conformer predictions. So in general, the key ingredient of conformer prediction is to define and choose a proper non-conformity function, which depends on the kind of predictor you're using. And the non-conformity function simply has to measure a sort of deviation between the true value and the predicted value. And the only assumption that is needed is that the data are exchangeable. In particular, in our application, we used a version of conformer prediction called Inductive Conformer Prediction, where a calibration set is taken out of the training set. So these points are not used for training the predictive monitor. And we compute the non-conformity scores on this calibration set. And we use this as an empirical approximation of the distribution of the non-conformity scores. And so we know how the deviation is distributed. And out of this calibration set, we are actually able for a new unobserved input to provide a quantification of the uncertainty and a prediction region, which is a band, a range of values that is guaranteed to contain the true value, the true target value with a fixed arbitrary probability that we choose. So these 2 properties are very important. And the uncertainty value itself does not have an easy interpretation. So we need a decision rule to decide which is the threshold value to accept or reject a prediction, to say the prediction is reliable or not. And for this reason, we decide to automatically learn an error detection rule by framing it as a binary classification problem. And the idea is very simple. We have the calibration set, we compute the measure of uncertainty on the calibration set, and then we label these points as correct prediction or incorrect prediction. So we have two labels here. And we learn how to distinguish a good prediction from a misclassification. So in practice, when you have a new input, you apply the predictive monitor, which tells you if it is likely to be safe or unsafe. Then using conformal prediction, you get an uncertainty value, and then you feed this uncertainty value into the subvector classifier, and it tells you if you can rely or not on this prediction. And when you think the prediction is not trustworthy, you reject it. So to summarize a little bit, the idea is the following. You define your model, you generate the synthetic dataset, then you train both the predictive monitoring and the error detection rule. The error detection rule can also be used to identify the points where the prediction is more uncertain, and you can use a sort of active learning step to add these points to the dataset and improve the performances. And in the end, you just simply evaluate the results. So to evaluate the results, we choose a benchmark of 6 hybrid systems, and to measure the performance, we have 3 important quantities. So we quantify the accuracy of the system, so how many predictions about safety are correct and how many are not correct. How many of the misclassifications are actually recognized by the error detection rule, and how many points we add to reject. The rejection rate is very important because we don't want our system, our technique to be overly conservative, because if we reject every time we reject a prediction, we have to go back to a safer and slower solution. So if we reject too many predictions, then we are actually affecting the efficiency of the system. So here this table presents the results of both the end-to-end and the two-step approach. And we see that the overall accuracy is very high in both methods. We also have very high detection rate. But in general, the two-step approach seems to behave a little bit better compared to the end-to-end one. And it is reasonable since the two-step approach is using more information from the dataset, because the end-to-end approach is actually discarding all the information provided by the sequence of full states. After only one iteration of active learning, we see that we have higher accuracy and, importantly, lower rejection rates, which means that we make less errors and we are able to recognize them by rejecting fewer points. So it improves the safety, both the accuracy and the efficiency. And with respect to probabilistic guarantees, we select a significant levels of 5%, and we see that in the initial setting, so without active learning, we satisfy the expected coverage as guaranteed by theory. And in the active learning case, we actually lose the theoretical guarantees, but in practice we see that we obtain actual better coverage and more efficient, which means tighter region. So the better performances are not reached because the active learning is more, the active learning model is more conservative. It's just because it's performing better on uncertain regions. We also tried to, so all the results here were analyzed on dataset where points were independent, so they were actually satisfying the exchangeability property required by conformal prediction. But when the system evolves at runtime, it is not guaranteed for states to be independent. So what happens when data have a temporal correlation, so when data have a sort of sequential nature? So we lose the probabilistic guarantees, and we try to see how the model was performing on sequential data. And we see that the accuracy overall and detection rate are still very high, but the results on average are worse than the independent counterpart. And again, the theoretical guarantees are lost, but in practice we see that the empirical coverage meets the expected coverage, which is a good feature, and it can be explored further. So in conclusion, we propose a technique for neural predictive monitoring that works well in a more realistic scenario. We saw that two-step approach works better, and it's also able to provide an accurate reconstruction of the true state. The online computational cost is very small because we just have to evaluate the neural networks and to compute the uncertainty value, which is a very efficient, which has a very small cost itself. And so this makes the technique suitable for runtime application. We enriched the predictor with an error detection rule and prediction regions that guarantees coverage. And we also introduce an active learning step that is able to enhance the performance on uncertain inputs. So as a future direction, we are thinking about exploring how conformal prediction are able to detect anomaly detection, so using some distribution shift information. We want to be able to work with fully stochastic model rather than only deterministic ones. And we would like to investigate the use of generative models for state estimation and the use of recurrent attention-based architecture instead of convolutional one to improve the performance on sequential data. So if you reach the end of this video, I thank you very much, and I hope to see you at the conference. Bye.